Hello class. Today we're going to do 5.5, section 5.5, the dot product. So first thing we want to do is talk about the definition. And so given two vectors, v and w, the dot product is, it's actually a product. And so we're going to actually multiply the two I components and then add that with the two j components. So let's do an example of that so you guys can see. Here are 4 problems that we're going to do. And so this first one, for A, it's asking us to do the dot product for v and w. And so that's going to be 2 from v times 5 from w plus a negative 3 from the j from the v vector times 3 from the w vector. That's going to give us 10 minus, I can't multiply today. 10 minus 9, which is going to give us 1. And so the dot product for this thing is going to be a value of 1. All right, so B, now it's going to be the dot product of w times v. And what we're going to see is that we're going to get 5 times 2 plus 3 times a negative 3. And that's going to give us 10 minus 9, which is equal to 1. So it looks like the commutative property may work here, but let's not make generalizations. The dot product of v times v is going to be 2 times 2 plus negative 3 times a negative 3. And that's going to give us 4 plus 9, or 13. And then D is an example of finding the magnitude. And so I want to show you something about this specifically. So if we remember the magnitude, it's going to be the square root of the I component squared, the coefficient, plus the j component squared. And so that's going to give us square root of 13. And we can see that the dot product of v with v and the magnitude are almost very similar. And so we'll see that there's a rule, and actually this is it right here. The dot product of itself is equal to the magnitude squared. So if I were to have done D and squared that, I would have gotten the same thing as I would have gotten in C. We end up seeing, like I said, the commutative property does hold true. And so the v times w, or v dot w, is equal to w dot v. Distribution of the dot product works. So if we have two vectors being added, and we're going to do a dot product to that summation, that's going to end up giving us this equation here. And then any vector times 0, or the 0 vector, is going to give us 0. So that's something important for you to know, and it will be useful as we move forward. All right, here's another bit of information for you to use. So angle between vectors. So if we had two vectors and we're going to be able to find their angles by using this formula here. Cosine of theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. So let's do an example of that so you guys can see. And I'm going to do it in pieces so that, and then I'll combine it and put it together. So in this example, I'm going to get u dot v, and that's going to be 4 times 2 plus negative 3 times 5. That's going to give us 8 minus 15, or a negative 7 as our answer. The magnitude of u is going to be the square root of 4 squared plus a negative 3 squared. And that's going to give us 16 plus 9 under the square root, which will be 25 under the square root, or 5. We need the magnitude of v. So the magnitude of v is going to be 2 squared plus 5 squared under the square root. That's going to give us 4 plus 25, or square root of 29. And so when we put this thing together, we get cosine of theta is going to be equal to a negative 7 over 5 square root of 29, which is approximately a negative 0.26. And that's going to give us a theta of cosine inverse of negative 0.26, which is going to be approximately 105 degrees. One of the ways to be able to look this pictorially so you guys understand is if I give you a graph of this, we're going to get 1, 2, 3, 4, 5. And let me elongate this a little bit. 1, 2, 3, 4, 5. Okay, so this first vector u, right here, it's going to go along the I4 and then down 3. So that's going to be this point right here. So the position vector is going to be this one. That is my u. 2, 5 is going to be up here. That's going to give us our v. And the angle that's going to be the result is this angle here. And we just found that to be 105 degrees by doing the math. But that's how you can see it pictorially to be able to find it and understand. Okay. Let's go on to the next thing. And we can see now we're going to determine whether two vectors are parallel. And so to see if they're parallel, there's two ways we can show it. One of the ways is to show that we have one vector is equal to a scalar times the other, or to show that the angle between the two vectors is either 0 or pi. So let's see if we can do that with this problem that we have here. And so if I look at v and w, doesn't w look like it's double v? So can't I say that v is equal to 1/2 w? And we can even check that, right? So if I go 1/2 w, isn't that going to be 1/2 times 6i minus 1/2 times 2j? And doesn't that give me 3i minus j, which is my v? This then means that yes, they are parallel. Now there's another way to do it. If you don't see the simple scalar multiplication, we can do it by finding the angle. And so by finding the angle, if we use cosine of theta is equal to the dot product of u and v with the magnitude of u times the magnitude of v, we can do this. We're going to get cosine of theta is going to be equal to 3 times 6 plus a negative 1 times a negative 2 all over the square root of 3 squared plus negative 1 squared times 6 squared plus a negative 2 squared, which is going to give me 18 plus 2 over the root of 10 times the root of 40. And that's going to give me 20 over square root of 400. And that's going to be 20 over 20, which is 1. Well, what is cosine theta of 1. Doesn't that tell us that theta is 0? And this is the other way to show there that it is, or they are, I should say, they are parallel. And it's this one because it shows that they are, in fact, the angle between them is 0 or pi. Okay. Now to determine if vectors are orthogonal, this may be a new word for a lot of you. Orthogonal simply means perpendicular. It's another mathematical term. Most of your math teachers should probably use the word orthogonal. I know I use it when I talk about it in class with my students. And so when we have something that is orthogonal, the angle between the angle between the two vectors is going to be pi over 2. And so another way to show it too is that the dot product ends up being equal to 0. So that's probably the easier way to do it. Instead of trying to find the angle, just show that the dot product is 0. So in this example here with v and w, we can do the dot product. So we can go v dot w, and we're going to get 2 times 3 plus a negative 1 times 6, and that's going to give us 6 minus 6, which is in fact 0. That's exactly what we needed to see from the dot product. So therefore, v is perpendicular to w. Okay? Very cool. The next thing is when we're trying to project, we're going to use these two formulas to be able to do that. And so I'm going to use it to create vectors that map on to the other. So I'm going to get the two vectors that create a vector, and I'll show you how to do that right now in this example. So we have the vector projection of v is equal to I plus 3j onto the vector w, which is equal to I plus j. And so we're going to find the two vectors, the two v vectors, v1 and v2, that are parallel to w. And v2 is to be orthogonal to w. So let me show you how this works. So then to find v1, we're going to use that formula, this first formula, number 10, and that's going to be v dot with w over the magnitude of w squared times w. So we'll be able to demonstrate that right now. And so let's do the first part, which is easier. Let's not deal with the w first. Let's just deal with this piece, and then we can address the w there in a second. So to do that piece there, I'm going to go the dot product. The dot product of these guys is going to be 1 times 1 plus 3 times 1 over the magnitude of w. So that's going to be the root of 1 squared plus 1 squared, but then it says to square that. And so that's going to give us, and then let's just keep w there so we can bring that along. We're going to get 1 plus 3, which is 4, over the root of 2 squared, and then times our w. And then that's going to give us 4 over 2w, or 2w. And so when we get 2w, now what we're going to do is we're going to replace w with its components, which is I plus j. And we see that the result is going to be 2i plus 2j. This is vector v1, and this is parallel to w. And remember, how can we show that they are parallel to each other, we need to show that the angle is 0. So you could go ahead and show that the angle is 0, and that would work for you just fine. Or we could show that they're a scalar of the other. So V1 we can see is just 2 times W. So the fact that we have this here, that demonstrates that it's parallel. All right, to find V2, what we're going to do is, it's much easier. Instead of doing a complicated calculation again, we can just use this piece right here. And so I'm going to go V2 is equal to V minus V1. And so we know that V is I plus 3j minus 2I plus 2j, which is going to give us I minus 2I plus 3j minus 2j is going to give us a negative I plus j, and that is our V2 vector. This is orthogonal to W, and we can check that by doing the dot product and showing that the dot product is in fact 0. I'm not going to demonstrate that right now, but there's one thing I do want to show you is what this looks like graphically. Let's see if I can do that for you guys so you guys can see. Okay, so what I'm going to do is W is going to be I plus, so I'll go 1, 2, 3, 4, and 5, and then we'll go 1, 2, 3, 4, and 5. And I might need one more, so I'll go 6 up here just so you can see it. Okay, so W we see is ij, so that's this point. And so if I go double that, so this is W, this little short guy is W, this longer one is my V1, so this whole thing here is V1. This little short guy, and maybe I'll do it in red just so you guys can see a different color. This one in red is my W. Then V, we know that V was 1, 3. That's right here, and I'll do that in a different color too. That's here. And those are both position vectors, W and V. So this is V. And then I'll do in green V2. And V2, what it does is it comes this way in this direction. So it ends up being V1 plus V2 is going to be the resultant vector. And we can see that this V2 is perpendicular right here to W. And so that's pretty cool. V1 is parallel with W, and V2 is perpendicular. I hope you found this beneficial. As always, all the best.